how to define a surface area. We actually did a little bit of it in Calculus 2 class when we were learning revolutions, remember? But it was not very optimal. We were figuring out some kind of rings, and the ring were used. In general, we'll try to approximate things with the things we know. So check this out. The idea is really, really interesting. Here is the surface area. I want to find the whole total surface area. This is want to find, by the way, want to find. I always put this joke at the very end so you feel excited. It's want to find area, not what you thought. So I put it once in the conference with like very respectful people there on purpose to see what they're gonna react. We want to find the whole thing. So how about we take the surface area and put lots of parallelograms everywhere, calculate area of each, because we can do that, right? And add them up together. So it's always the sum of stuff. When we had area below the graph, it was the sum of tiny things, rectangles or whatever we wanted to use. When it was volume, we had cubes and other objects we liked. So it's always sum of things. Here's the idea. What if I will find the area of those tiny pieces and then just like scales on the fish, I'll put it on top of the fish and say, oh, this is surface area. Surface area is only the outside part. I don't need the volume. How to find this area? Oh, there was some connection with vectors. Remember that? Yes, you do. So some connection with two vectors. What kind of product it was? Do you remember? Cross product, good job. That is like exam 1. It was cross product of two vectors that gives you area of this parallelogram. But what kind of vectors do we need in this case? That is kind of more interesting idea. I want the vector to be very close to the surface I'm talking about. And this vector to be very close. What kind of vector is the closest one? So here is like a surface of my hand. The sticking out was the normal vector, but I want the one that's, and that is the opposite of being very close to it, right? The opposite of being very parallel to the surface. Which one? Tangents. Tangents are the one that's very close to the surface. We even use tangents and derivatives to approximate stuff, if you remember approximation, linear approximation. So I'm not gonna just multiply r and r. I will take derivative r with respect to, well, u usually goes first, u, and then with respect to v and do the cross product of these two. That is the idea here. So that's what I found is a very cool idea in general. This is how it looks if you zoom in. If we consider the don't do that. If we consider the parametric surface S described by the equation, let's write down this. R, U, comma, V. We just learned in the same chapter parametrization using U and V. So remember we learned before R of T, but now we're adding a dimension U and V. And I even showed you this idea of the cute game. Let me show it to you again, especially if you missed the class. With parametrization of a surface, we're increasing the dimension of from one vector to another vector. Instead of R of T, which we had before, we're going to have two vectors. This is left joystick and the right joystick, and then you spin each. And while U is changing and V is changing, some surface is being created because you're pointing at it. Before it was just T, which is usually time. When time is passing, something is being created in 3D. Now we have two variables. It can be angle and time and distance, viscosity and heat. So we want to increase the dimension because that makes it's more interesting and more applicable. So we have R of U and V, X, Y, Z, and all of them depend on U and V. On a domain D. Domain D, let's put it this way, for example. R, this helps us to describe this beautiful 3D shape. I want to find a surface area of that. So D is a domain, remember that, right? It's a domain. Like so. That means if I find some kind of square in a domain, it will go on top of the surface. How is it working? So this point is on the floor. It's also domain in terms of u and v. So it will go on top of the surface S at some point. So I want to accumulate all those points to find the surface area. But points is not a very smart idea. The smart idea would be using shapes we know. And we know squares. And we know parallelograms. And we know triangles. So triangles are actually used in mapping the world maps and so on. And in other stuff too. So the idea was, let's create a grid. Do you know what grid is? When you actually like dividing things into sectors or segments, grids. So we're gonna divide D into sub-rectangles. And then we're gonna choose one or any, it will be random one. And then we're gonna map that rectangle to the surface. Here it is. Interestingly, see it bends. So it's now, it has some kind of angle. It bends, it curls. Now, we want to keep describing it. So we will describe R sub U, that's derivative of R with respect to U, partial derivatives. R sub V, that's derivative of R with respect to V. Those will be tangent vectors. Tangent vectors. Write this down. This is important. Let R of U depend on U and V, and RV depend on U and V. Those are tangent vectors. Why are we using tangent vectors? Because that will help us to create the area of that rectangle parallelogram. And tangent vectors, if they want to mapping very close to the surface, even though it will have some angle, it's still good enough if you zoom in. Let me wait a little bit. Then, when you do that, this is the zoom in picture. This is the surface, like a, actually it's not smart. This is like a curtain. Say it's a curtain or a wave. I'm creating this yellow square or parallelogram. And I will say, let me find the area of this instead and say it's a good approximation. Well, those vectors are tangents. So tangent from the point, tangent from the point. Parallelogram in tangent plane, here it is. So it's taken out of here, check it out. This is just one of those examples. The exact one will be curved. I'm creating the approximate one, and it will be close enough. At least that's what we claim. The area of that patch, we call it patch, very nice way to see it, can be approximated by the area of parallelogram determined by those two vectors, derivative of R with respect to U, derivative of V with respect to U, times small changes du dv. That is the idea. And we proceed with this idea and the formula. You can write down this formula. We will find the area of one parallelogram, and then another one, and another one, and another one. Adding them all together will give me approximation of the actual surface area. But the more I have them, the closer they are to the actual surface. That gives me the limit, remember? Limit of the Riemann sums gives you integral. And that's how it's always happening the same way. We're adding up together some things we know. In this case, areas of parallelograms that were created from tangents. Cross product of tangent creates the area of that parallelogram. Did you understand this idea? Cross product. So let me write down. Write down the formula, and I will write down steps. I wanted to have this nice notes. So steps. I feel like the formula is overwhelmed with different notations. So step 1, you find derivative of R with respect to U. You can put prime or not. Derivative of R with respect to V. Find that. When you found those two, you calculate the cross product of those two vectors. Remember, that's going to be a vector, right? That is cross product. But of what? Of derivatives. That's going to be an important thing to remember so you don't mess up. It'll be upsetting if you calculate the whole cross product and then you chose the original R. You have to have R with respect to U, R with respect to V. And the third one, you find the magnitude of that. Find magnitude of RU cross RV, and you know what it is. It's a square root. Do you remember square root of what? Does anyone remember square of what? Partial derivative of whatever we already have. How cool is that? So, no, partial derivative, we already found it. So we're squaring and adding, squaring and adding, squaring and adding, remember? Yes. Well, we're gonna have example. If you don't remember, it's fine. But you kind of should remember that for the exam. Okay, did you say? Magnitude. What is magnitude? The formula for magnitude. Of?
The vector, derivative of the vector squared plus derivative of the other vector squared.
So derivative or original one? That's my question.
Derivative.
Derivative squared plus derivative squared plus derivative squared. Do you agree?
Yeah.
Okay, good job. Good job. For what I was trying to say. Oh, and now you integrate. And now you integrate the result. So you found that answer. You know, I like to put magnitude in this notation, du dv. So it has 4 steps. The most important, the first 3 steps, and then you integrate, and you use all the knowledge we learn how to integrate. If you want to do parametrization, do that. Polar, do that. Spherical, do that, and so on. Well, polar will be popular here. Another formula, that's what I put, or. Another formula, if you have z equals, if we already have the shape of the function as z equals blah, 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 then it's actually easy to do this way, which is still double integral. And now we have derivative squared plus derivative squared plus 1. I don't know. I don't recommend to memorize one more formula. That's what I put here. I personally think it's easier to do the problem the first way instead of memorizing a new formula. But both will work. And I'll show you an example when this second way is faster. But if you do the first way, it works too. The thing is, cross product takes time. So that's why it's kind of questionable. Sometimes it's an overkill. So z is given, or you can find, then you can just proceed with this formula instead of creating parametrization and then finding cross product and so on. Questions about this? And you see derivative squared plus derivative squared plus derivative squared of z, but that's 1. So that's where it's coming from. Example. Before showing you the picture. Example 1. Find area of S, where S is helicoid. What is helicoid? You don't have to know, but it's kind of cool word. Helicoid with equations. R of u and v equals. So parametrization is already given. In this chapter, we're teaching you how to create parametrization, and I'll show you more examples like this later. But you're lucky if it's given. That's the good news. Remember, like even in the previous exams and materials, if R of t is given, you feel happy. So that's the same thing. It's nice if it's given. U of v, u cosine v, u sine v, v. For you to know u and v is not some kind of secret notation that you should always keep. You totally could rename it to be r and theta, and it's going to be r theta, and r. Like that's not, oh, it's actually theta. It's not forbidden. U and v is just very popular. U is from 0 to 1, v is from 0 to pi, which gives you the idea that v is the angle, u is a distance. Can you guess what it is? Because helicoid, we know about helix. But what is helicoid then? And also you can see the relationship. What these two are doing, u cosine and u sine. What do you think they are doing? So remember, you know what's going on here? This is x, y, and z, right? So if x and y are r cosine theta and r sine theta, what is being sketched in 3D? Circle in 2D, right? And it's a completed circle in 2D xy plane. And then z is keep growing up or down. So that becomes what? Spiral. Well, very interesting actually that you thought about cylinder as well. It's a spiral, but that's called helix. So what is helicoid then? Helicoid is the helix that has width. So it has surface area, which we're going to calculate right now. Sometimes people compare it with like tilted stairs Actually, civil engineers will be building that a lot. So helicoid will be quite often everywhere. Basically, it's a strip if you think about that. So that is a cool idea. Helicoid, this is how it looks like. Helix with some width. So they want us to find the surface area. So this is a surface, see, area, surface area of this object from u from 0 to 1, v from 0 to pi. And I'll just, well, you should help me with these steps here. So my note, I actually decided to Google it, why it's called differently. The word helix comes from the Greek word twisted or curved. That's helix, right? A filled-in helix, for example, is a spiral. And that is a surface called helicoid. Pretty cool. I found it pretty fascinating. It actually has lots of cool properties. You can fold it together into cool shapes. So you will see some applications with that, for sure. Go back here. Okay, now I want to show you some cool steps that will help you with your homework, but I don't like how they explain it in the book or in the homework with these specific problems. So I want you to have nice steps, which you don't have to follow, but you know my philosophy. If you freak out and you know steps, you can do that. I already mentioned some of them. What was the first thing to do? Find RU, RV derivatives, right? So solution, let's do step 1. Let's find derivative with respect to u, derivative with respect to v of r. The thing is, if r is not given, you have to create it. So at least we skipped that step. That kind of sounds pleasant. Let's go back and see what my r is. U cosine, u sine, v. So who can give me r with respect to u? Is it going to be a vector? Is it going to be parentheses? Is it going to be a sum? What is that? Who knows? A vector. We're just taking original vector and differentiating it, but only with respect to u. So u cosine v gives you cosine v, thank you. U sine gives you sine v, thank you. Some students told me they don't like that u and v looks more or less the same. So make it sharp looking v, and you can add some hats. And u has a tail. That's quite important. And the last one, what's the last one? 0, because it was u, derivative of, oh no, it was v. Derivative of v is 0. That's a vector, remember? Second one, that's one with respect to v. U cosine gives you negative u sine v. Amazing. Next one, u cosine v. Amazing. And 1. Good job. All agree? Any questions? Yeah? Oh, nice. People have thumbs up. That's nice. Now, next step. So we did that. Step 2. What did we do? What did I say we should do now? Oh no, the cross product. RU and RV, cross product. There's a cross product calculator I found online, actually several, but on the test you cannot use it, so you have to figure it out by yourself. Do you remember how to do cross product? That's a good review for the test. IJK, J negative product, good. So let me put a note if you need that. Good job. What is the next line? Anyone at the end? People at the back. People at the back, are you okay? Oh, what? Are you? So can you read me? Cosine v, sine v, 0. Is that correct? Agree? Yeah, good job. Thank you. And the next one? RV. Who wants to read me RV? That will need more space. Negative u sine v, u cosine v, 1. Agree, disagree, comments? Thank you. As you can see, sometimes I put parentheses, sometimes not. So you can do both. And now we're actually calculating determinant of that. Review before the exam. That's a good one to do right now. What do we do? And you can do it in two different notations. Do you remember? You can do I multiplied, then minus j multiplied and k, or you can do vector notation. I think you guys mess up less when there's a vector notation. I notice that even there is not a vector notation, well, they're both vector notations, but I notice in this notation, you mess up less. You don't lose signs. So let's do that one. I will be what is the calculation for I? Sine v times sine v, that was ugly, v times 1 minus u cosine times 0. Good, I will skip that. Next, j component. So let's see, cosine v times 1 minus times 0. So I will skip it. Yes, no? Negative. Good job. Thank you for noticing that. Negative. Finally, the last one. This one. K component actually will not have zeros, unfortunately. Cosine v times u. Cosine v. Remember cross product. Cosine v times u cosine v. So that is what? U cosine squared, right? Minus, and then you have u sine times sine. U sine squared, correct? No. Plus. Minus gives you plus. And that's a good news. Why? Because we can simplify sine v minus cosine v, and then u. What happened with cosine square and sine square? It becomes 1, exactly. Okay, so we found cross product. Now I am out of space for some reason. That was step 2. Step 3, what should we do with step 3? Magnitude. So you will have, this is what we call ds at the end of the integral for the formula. So, okay, let me actually review what formula we're using. We're using this formula over here. We found this thing, cross product. We're finding magnitude of that. This is my, so the tail is my ds. So we're only one step away to figure out ds, this thing. So let's do that. ds is a square root of. Now what do you think we should do? Square them all and add together.
Yeah.
So are we taking derivatives then, or we're not? But you guys said we're taking derivatives. Wasn't like derivative square plus derivative square plus derivative square. But so we do that or we don't do that? We don't do that. Remember that you're conflicting it with line integrals probably, or some other formulas. When we had magnitude of the derivative, then yes, you can do derivative square plus derivative square plus derivative squared. But we already found it, right? Then we found cross product, right? So now we're squaring, adding together. Do you all agree? Just let's make sure we don't get confused with that. It'll be upsetting if you're doing everything correctly and then this like very small formula you mess up. So we do sine squared plus cosine squared. I'm ignoring negative sign because it's squared. Plus u squared. Agree? Magnitude. That simplifies nicely into 1 plus u squared. Looks amazing. And the last step is actually to integrate. Step 4, we're looking for surface area. So some people call it A of S. There's not international notation here. People call it anything. So just get ready to see different notations in different books. Equals double integral ds. That is a short notation of the formula over d. So we found it. Double integral so the tail ds, maybe put it in the box. That's basically the most important part here. Here, ds is found. We found ds. 1 plus u squared. And then we have du dv. Du dv. I will stop here for a second and ask you what do you think about that. Does that make sense, people over there at the end? Good job. So, almost done. Try to concentrate. I know you feel tired. I can feel it. That's why it's hard to motivate people the last week of classes, but like, try your best. This is very interesting. Surface areas, how cool is that? So, what are integral limits of integration though? We need to choose what to do there. Maybe we can use polar equation, maybe some other parametrization. Or, what do you think we should do here? We have them. To be honest, that's just a lucky situation they were given. If not, then you will have to create them yourself, and you can use Cartesian, polar, you choose. But in this case, it was given u and v. U is from 0 to 1. V is from 0 to pi. And your job is to integrate that. And I'm going to give you the answer. So I'll put ... And the answer is, do you know if the answer should be a vector, a function, or a number? Why do you think it's a number? Because it's area, exactly. It even has units, right? The answer is pi over 2, square root of 2, plus ln of square root of 2 plus 1. If you're curious, this integral was solved using some calculus 2 material. Do you know? Can you guess? Table integral, actually, that's what I thought right away. I was like, let me just find it in a table, and I did. I found it here for you, so those are in my notes. It is a table integral. But do you know how table integral was created? Someone did it. Someone solved it. Yes. If you see square root of 1 plus stuff squared, it reminds you some trick inputs, right? So trick substitutions. So which trick do you think is that? Tangent. Good job. Who has good memory? 1 plus stuff squared usually is tangent. So I do have solutions for you where people use tangent. You substitute x equals tangent, dx becomes secant squared, blah, blah, blah. It's interesting if you like that kind of stuff. Then it's not too bad. But it is a table integral as well. That takes you to the calculus 2 ideas. What do you think about this? Yes?
On the exam, are we gonna like have integrals where we have to do tricks of them?
When you have to do what?
Are we gonna get like problems where like the integral we have to do like ends up being tricks of?
Oh, no, we don't. We don't test you on integration of that kind of stuff anymore. We test you in calculus 2, and as I can see, you passed. So now we try. Well, we still testing you on solving triple integrals, as you could see in previous exam. But that reminds me, that was a good question. The question was, will we have complicated calculations like this in calculus in this exam? I actually left it out as a double integral, but do you know that I can break it into 2 single integrals, right? One for dv will be, so let me write down dv, 0 pi dv, and then 0, 1 du, 1 plus u squared du. What does this integral give you? Pi. Good job. The distance of the interval. And then this one you actually can struggle with, but how do you do it during the exam? You can use graphing calculator. Yeah. So that answers your question as well, even if it's crazy. Now you can use graphing calculator. What if, just like a random question, what if graphing calculator cannot do it for you? Trick substitution did not work. What if you paid 6 digits for this project and you end up with this integral and you have to present the result? Do you know what you're gonna do? Praying might help. What else? It's on the class. You were hired. They pay you 6 digits and they don't care how you do it, right? It's very realistic idea. You are presenting results and they want you to give a number, whatever that is thing, so they can continue with approximation of how much to order for Walmart for the next week, how much antibiotics to order for the hospital, statistical approximation of the earthquake. That relies on that number. How would you find it if it's not a table integral, if nothing worked and calculator cannot get it? What do you think you should do? The answer, usually people say Google. Okay, you Google, did not work. What do you think you should do? There is one more method we learned last semester. Which one? USAP did not work. But thank you for mentioning it. Some kind of what?
Is it like series or something?
Series? That's very close. What do you think? You are close too. Some kind of approximation. How? Numerical approximation. It's using computer program to figure out Simpson's rule using parabolas, left endpoints of rectangles, any triangles if you want to do with triangles. There are methods like that. Euler's methods, any kind of way you have approximation of that. And then you still get the answer and get 6-digit salary and then you go travel a lot, right? Good job, people. I will see you right now in the office hours. I'm going to office hours right now. And I will see you on Thursday.